It's just wherever it is distributed. So spheres still, all right? So I like to do that one, and then and we can do a variation of that as well to make it a little more interesting. And then I'm gonna move on to doing very long wires or cylinders, maybe hollow cylinders. So then we're gonna go to cylinders, okay, and wires and cylinders. So let me do the case of the sphere, but a dielectric or insulating sphere, right? Where in that case, the electric field inside the body of the sphere just doesn't have to be zero. It could be something. And as you'll see, it'll be something. Okay. And we don't really need that, I think. So I don't know if this is 5 or 4 or 4. Okay, so so a dielectric that's insulating, right? Solid. Solid means that it's either solid or hollow. Hollow means there's a hole cut out inside. Solid means it's, the material is all over the place. It's not hollow. So dielectric solid sphere of radius A, and let's do this one, uniform charge per unit volume rho. So rho is the charge per unit volume. Okay? So, and calculate the electric field everywhere in space. So we're given a sphere of radius A, right? And all over the sphere, there's a charge per unit volume rho. So there are two regions of interest. Somewhere inside the sphere and somewhere outside the sphere. So let me do inside the sphere first. So I'm going to do inside. That's when R is less than A. So I'm looking at a point, say, right here, which is at a distance R away from the center. And notice that this R is less than the radius A. Okay? So we're given a sphere. We then imagine, so we're going to use Gauss's law to solve this problem. So we imagine a Gaussian surface, a closed surface, which is called a Gaussian surface. What is the surface that we imagine?
Sphere.
A sphere. Concentric with this one, having the same center, right? And passing through what point? Should I imagine a Gaussian surface passing through this point, or maybe here, or so where? At the point that we're asked to calculate the electric field. So I'm going to draw my Gaussian surface. It's the one in red over here, supposed to be a sphere. So this thing in red is the Gaussian surface. Okay? And then I write Gauss's law. E, the integral of the electric field over that Gaussian surface, right? throughout the area of that Gaussian surface is going to be equal to the total charge inside that Gaussian surface divided by this constant. So this just becomes, for spheres, E times an area. What is the area that I need to multiply this electric field magnitude by?
4 pi squared.
Should I say 4 pi r squared or 4 pi a squared? R, because r is the radius of the Gaussian surface, and I'm multiplying this electric field at the Gaussian surface by the area of the Gaussian surface, right? And the Gaussian surface is the one in red with radius r. Maybe I should make this r over here red. Maybe that'll make it easier. And then A is the radius of the actual problem, right? Of the actual sphere that we're given. Okay, what should I write down on the right-hand side of this equation? And before I forget, I like to put that one so I don't forget at the end to include that constant in the denominator. So, what should I put in there? What I want is the total charge where? Enclosed inside what?
The Gaussian surface.
The Gaussian surface that I imagine. So look at my surface in red. I want all the charge inside that surface in red, because that's my Gaussian surface. So the charge that I want is all of this charge. I'm going to shade it. This is the charge that I want, because that's the one that's inside my Gaussian surface, right? So what is that charge enclosed? I know the charge per unit volume. Every little bit of volume or unit volume, right? If that's a unit of volume, the charge in there is rho. So what's the total charge that would be contained in that sphere of radius r if the charge is uniformly distributed throughout that volume and the charge per unit volume is rho? So what would that be? What do you say? Rho times, so is the charge per unit volume times what? Times that volume. And what is that volume? What is the volume of a sphere of radius r? 4/3 pi r cubed. Is that something you have to, is calculating this charge enclosed something you have to memorize? Or is it something that you understand enough that you don't have to memorize it? Does it make sense to multiply rho by 4/3 pi r cubed?
So
Or does it not make sense?
rho is just like a small section of the sphere, and then 4 pi r cubed is the total volume of the sphere. Is that why we did that?
Exactly.
Does that make sense? Okay.
So for example, suppose, rho is the charge, it's the number of coulombs per unit volume. What is the unit of volume? What's the unit of length?
Meter.
Actually, this is the unit of length, 1 meter. This is a meter stick, 1 meter long. So this is the unit of length, right? So what would be, what's the unit area?
Meters squared.
A meter squared. So it would be an area where you have, let me show you 1 meter square. So that's 1 meter high, and that's 1 meter. So so this is 1 meter, that's 1 meter. This area here is 1 meter squared. This is the unit of area in the metric system. This is the unit of length in the metric system. And the unit of volume in the metric system is a volume of 1 cubic meter. So that would be, well, not quite, well, so up to here. Well, not the whole length of this thing, so up to here. and then sticking out over here. Can you imagine this box 1 meter on each side? That's the unit of volume. So suppose that this room were filled up with charge, right? So every one of these cubes, 1 meter on a side, would have a charge of rho. That's the charge per unit volume. It's the charge in 1 cubic meter of volume. So the charge contained in this box 1 meter on each side is rho. So what will be the total charge in this room? It's like, well, it's uniformly distributed, right? So it would be like the charge in this unit volume plus the charge in the next unit volume, which is the same because rho is uniform, plus the charge in the next unit volume, plus the charge in the next unit volume, plus the charge in the next unit volume. You might as well just find out the total volume and multiply by rho. And that gives you the total charge contained in that volume. Yes? If I wanted to know, suppose the charge is distributed uniformly over this whiteboard, from here to there. Suppose I want to know all the charge over there, right? Well, the charge per unit area is defined as sigma. It will be the charge in here, in this area. Well, I can take another meter square, and that will be another sigma. And then another meter square, and that will be sigma. And so to get the total charge, I can just multiply sigma by the total area of the board. So the total charge contained over here is the charge per unit volume times this volume, which is, well, for a sphere of radius r is 4/3 pi r cubed, and this is the charge per unit volume. So now notice, then the next line is the answer, right? The next line is the answer. This is a problem that I can, this 4 pi's cancels this 4 pi's, this r squared cancels r squared from there. So the answer is this. Right? And if the charge is positive, the electric field is going to be pointing radially outwards. I can do this and put in a unit vector in the radial direction. If this charge is negative, it will be pointing radially inwards. But if this throws you off in the moment, just forget about that. This is the magnitude of the electric field at that point, at a distance r away from the center of the sphere. So notice, this is a 3-liner. Gauss's law is already 1 line. This is where you put in the physics of the problem. And from here to here, that's not physics, that's just algebra, right? Solving for E in this equation. Quite powerful. Imagine if you had to calculate the electric field over there due to all of this charge, breaking it up into dq's and dq of r squared, the directions of all those vectors, it would just drive you nuts. It would just be a much harder problem. So now let's calculate the electric field outside that dielectric sphere. So that'll be B. So now we want outside. That's when r is going to be greater than the radius of the sphere. So here is the sphere, or radius A. I got charge all over the place, right? Rho. And I want to know the electric field right there. I'm going to use the same color. So now this is R. Notice that R, I want to know what's the electric field right there. So notice that R is greater than A, which is why I write R greater than A. So what do? I imagine a surface, which we call the Gaussian surface. What surface do I imagine? A sphere. Passing through the surface of that sphere should be passing through what point? Through that point where I'm calculating the electric field. So then this is my Gaussian surface. Remember, this surface doesn't exist. We're just imagining this surface. And then we write down Gauss's law. Okay? And then this, for the correct surface that you imagine, in the symmetry of the problem, this integral just becomes a multiplication of two quantities. So it is the magnitude of the electric field at the Gaussian surface multiplied by which area? Should I say the area of the Gaussian surface or the area of the sphere that was given?
The Gaussian surface.
Gaussian surface, which has, so what should I write down?
4 pi r squared.
4 pi r squared. Good. And then what is the total charge inside that Gaussian surface? So what should I write down in the numerator over there on the right hand side?
You should write rho 4/3 pi r cubed. Oh, I cubed.
By who cube?
A.
Because this charge is only distributed up to radius A. There's nothing over here. This is vacuum. So there's no charge in there. So the charge that it's the total charge inside the Gaussian surface, which would be the total charge in the sphere. But the sphere has charge only up to radius A, not up to radius R. So notice how in this part of the problem, this R on the left hand side is the same as that R on the right hand side. But in this other part of the problem, notice that this R is different from the R that goes over there. And you need to understand why they're different. It has to make sense. Think about it until, right? Because what I want in here is the total charge inside this surface in red. Well, the only charge inside that surface in red is the charge in this sphere. But what is the charge in the sphere? It's the charge per the volume times the volume of the sphere, which is 4/3 pi A cubed. If I write R cubed over here, then I'm saying that this charge is distributed all the way up to radius R, which is not the case. It's only distributed up to radius A. So it has to make sense. And then the next line is the answer, right? So what do? We say, okay, I see f of pi and I see f of pi. That cannot be canceled with that. So this will be rho A cubed divided by 3 epsilon naught R squared. So this is outside, and this is inside the sphere. And if we wanted to do a graph of electric field magnitude plotted on the vertical axis versus the distance away from the center, right? The only radius of interest is the radius, that tells you the, A. So any value of R over here is less than A. That's inside the sphere, right? And any value of R over here is outside the sphere. Notice that what happens if I take this result? What would happen if I take this result and I let A be equal to R? Then this expression will become, that will be like the electric field at the surface, right? It will be like rho R cubed over 3 epsilon naught R squared, which is rho R. Actually, I should do it not like that. I want R to be A, actually, so then this will be A cubed, and this is 3A squared. So this will be rho A over 3 epsilon naught. And if I do the same for this result, then the electric field will become rho A over 3 epsilon naught. And that's the same as this. So inside the sphere, the electric field is given by this expression. So what is the behavior of the electric field with distance r? Is this a parabola? Is this a circle? Is this an ellipse? What's up? You tell me. What is this an equation of? What should I sketch over there?
A line?
E is on the y-axis. R is the x-axis. So what is it?
A line?
A line. With what slope?
Rho over 3.
Rho over 3 epsilon naught. With what y-intercept?
0.
0. Exactly. So it should be a line like this. With positive slope. And I know that, when you get to the surface, right? That's rho a over 3 epsilon naught. Now, when I step outside the sphere, the electric field is given by this. Now, what is this a graph of? And what is the value of the surface? On the surface, it will be this, right? So I start over here. So what is the graph of, this is like y, right? And this is like x.
Isn't it like,
This is essentially y equals something, whatever, divided by x squared. What does that look like?
doesn't it look like that? I don't know how to say it. It just forever approaches 0.
Exactly. So the electric field actually grows linearly with distance from the center up until you get to the surface. Outside of that, then it drops as 1 over r squared. Right? So this one here is proportional to r. Here is proportional to 1 over r squared, right? So that's the electric field inside a dielectric sphere. Now, remember what the graph was for a metal? For a metal, charged, capital Q is the total charge, that was solid, right? Because it's a metal in electrostatic equilibrium, where did the charge go? To the surface of the metal. And what did that make the electric field inside the sphere? 0. So in that case, the electric field, for the case of the metal, was 0 inside, everywhere inside it was 0. And then boom, it made a jump, and then it went like this. But if it's not a metal, if it's a dielectric or insulating material, the electric field is 0 at the center, but then as you walk away from the center towards the radius of the sphere, the electric field is getting bigger, biggest. And then it drops off. Once you step outside, it's like the electric field is the same as if all that charge were concentrated at the center. In fact, what is the relationship between the radius of the sphere, the charge per unit volume, and suppose the total charge is Q? What is the relationship between those quantities? The total charge of the sphere, the radius of the sphere, and the charge per unit volume. Suppose I tell you rho is brr, and the radius is brr. What's the total charge? How do you get it? Rho times what? The volume, which is? Correct, 4/3 pi a cubed. Notice that outside the electric field we have rho thirds a cubed. What is that? That's a cubed, rho, and a third, right? That's that, right? So notice that rho a cubed over 3 is q over 4 pi, right? So what if I take this and I replace it for this quantity here? Then I'm going to get rho a cubed over 3, which is q over 4 pi. And then I have the epsilon naught. And then I have the r squared. But 1 over 4 pi epsilon naught is Coulomb's constant. So notice that as soon as you step outside this dielectric sphere, in fact, as soon as you step outside the sphere, it doesn't matter if it's conducting or dielectric. The electric field outside is given by the same expression, and it's given as if all the charge is concentrated at the center of the sphere. Yes? No? Okay, so, just notice the difference between the dielectric sphere, the results for the dielectric sphere, and the metallic conducting sphere. Right? So notice the difference between them. Here you have, well, inside and outside the sphere. And every calculation that I've done, boom, 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 we're done. Right? 1, 2, we're done. That's it. It doesn't take much to solve these problems. You can do this in the back of an envelope. Calculations. And then this is just recognizing, that this is the equation. If I replace this E by Y, and this is Y equals something times R. So this is like Y equals mx, right? So that's a line, that's the slope. So the slope of the line is this, right? 3 rho. So the slope of this line is that. Let me say something. Can I erase this now?
I have a question.
Yes?
So the electric field will be the strongest on top of the surface.
On the surface, for this one. And this one really, in the case, see, in this case, the charge per unit volume is distributed from the center all the way up to the surface, but not quite on the surface. It's like, up to there. In the case of the metal, the charge was on the surface. And that's why we had this discontinuity here. But over here, it's still discontinuous in some sense, right? That's still a kink. Right? But you can argue it's like, there's still a little kink over here. So, but the value here is the same as that because it's like this charge is all the way up to the surface, but not including the surface, kind of. Very, very close to it. Okay. Let me erase this and discuss. And let's do a little aside problem. Can I erase this? Sure. By the way, some of you are transferring out in this fall? Yeah. All right. Exciting times. New challenges. Cool.
That's great. You talking about
You both are great. In the best way possible. Thank you.
So Newton, Isaac, right? The British guy, wrote M1, M2, distance R, and what did he say about two objects with mass M? They attract one another, right? And they attract one another, and what is the name of this force? The force of gravity, right? And if this force happens to be 3 pounds, then that force is also going to be 3 pounds. If this force is, then the other one also feels a force this way, right? Of the same magnitude. And Isaac Newton wrote an expression for the force of gravity, right? He said the magnitude of the force of gravity, maybe I'll do this, is what? Do you remember? Anyone? What's that?
G.
Capital G, yeah, there's a constant, correct?
M1 and 2.
M1 and 2, you multiply the two masses and then you divide by? R squared, correct. Coulomb, he's honored with his last name now being the unit of charge in the metric system, right? Coulomb said, if this charge is Q1 and this charge is Q2, then separated by a distance r, because electric charges in nature can be plus or minus, we have two possibilities, right? Then the force, the electrical force between them could be one of attraction or one of repulsion. Whatever, okay? So let's make them plus minus, so this is now the electrical force, right? And again, if this force here is, whatever, it'll be the same value over there in magnitude. Not the same force because they have different directions. And same thing over here, right? If this is whatever, then that'll have the same magnitude but in the opposite direction, right? Now, what was the expression that Coulomb wrote down for the magnitude of the electrical force? So, analogous to this, K, Q1, Q2, just the magnitudes, right? Divided by R squared, right? And K, by the way, could also be written as 1 over 4 pi epsilon naught, right? And then Q1, Q2 over R squared. So, if I look at this constant that multiplies the two masses and the divided by the separation distance squared, right? And I look at this constant that multiplies the two charges, then I can actually do something interesting, right? I can say, wow, there's a constant times the two masses divided by the distance squared. Or there's another constant multiplied by the two charges divided by the distance squared. So it's like G, the universal gravitational constant, is playing the role of Coulomb's constant, which is 1 over 4 pi epsilon naught, right? And Gauss's law says that the integral of the electric field, right, over the Gaussian surface is Q enclosed over epsilon naught. Well, there is a Gauss's law for gravity as well. I can write, for the case of gravity, I'll say this. It's the integral over the Gaussian surface. But instead of calculating electric fields, what do you think replaces electric fields in the case of gravity? Gravitational fields, right? Which is denoted by G. And then you dot it with the area vector of the Gaussian surface. And then we have, one of the messages, the main message of Gauss's law, see this, is that the thing on the left is produced by the thing on the right. So the main message here, and then how do you do the details, dielectric sphere, cylinder, point charge, hollow thing with, right? This is saying that electric fields are produced by electric charges. So if I run into you 10 years from now somewhere, and you tell me, oh, hey, what's up? I took your Physics 280 class. And if I ask you, did you learn something? I say, well, yes. So what did you learn? Electric fields are produced by electric charges. I'll be very happy. So, what produces a gravitational field, according to Newton?
Mass.
Mass. So therefore, instead of having charge enclosed, it's a mass enclosed. And then I have this constant, and then what do I do with it, right? Then I say, okay, G is like 1 over 4 pi epsilon naught. So 1 over epsilon naught is like 4 pi G. So you replace the 1 over epsilon naught by 4 pi G. But there's another thing that we need to take into account. Electric fields can be pointing away from the charge if the charge is positive, or towards the charge if the charge is negative, right? We know that in the case of gravity, the gravitational fields are pointing which way? Towards the charge. So we just, put a minus sign. So this is Gauss's law for gravity. So let's consider the most beautiful object with mass in the universe. Planet Earth. Besides my wife. Okay, so planet Earth. So here's planet Earth. So the Earth has a radius, which I've been calling like A, right? And the Earth has mass everywhere inside. It's like a solid. The mass distribution is not uniform because the density changes with depth and so on, right? But the mass of the Earth is, it's everywhere throughout. It's not hollow. It's not like you drill a hole and then you fall and you end up in China on the other side of the Earth, right? So it's solid, right? So that's the mass of the Earth, right? Suppose I want to find out what the gravitational field is generated by the Earth, on the surface of the Earth. Let's say here in this room, a meter above the ground. Actually, everywhere in this room. So let's say we're interested with right there, at a distance r, which I'm going to approximate as the radius of the Earth, right? So what is the gravitational field over there? And then I say, oh, I'm going to use Gauss's law for gravity. Right? So I'm going to use this. And so what do? Well, it's a sphere, right? So I'm going to imagine a sphere, right? Yes? Now, the gravitational field is actually, we know the direction, it's inwards, right? But the area vector is going outwards from the surface, is this way. And the angle between the Earth and the gravitational field is 180 degrees. So this is how we do it, right? So then you say, okay, so it's the integral. Now, how do I do this dot product? It's the magnitude of G, magnitude of it, right? Which is a positive number, times the magnitude of the area vector, times the cosine of, how do you do a dot product of two vectors that point in opposite directions? What's the angle between them?
180 degrees.
180 degrees. That equals minus 4 pi G. And what is the total mass enclosed by my Gaussian surface? Just the mass of the planet, right? So, if I'm very, very close at the same distance away, right, then the gravitational field should be the same. So I take this outside, so this is G. The cosine of 180 degrees gives me a minus 1, and then I have the integral over the whole surface, which is that. And then I have minus 4 pi G times the mass of the Earth.
Sorry, sorry, did you say the negative from the G was because of the direction of the vector? Okay.
Of the electric field. I mean, of the gravitational field. It's towards the mass as opposed to away. I mean, normally what we say, we kind of do that if you have a sphere like this, a radius r, or radius a, and this charge is negative, right? Technically speaking, right, when I draw my Gaussian surface, I have to say, oh, the electric field is this way. The area vector is that way, right? And then this is 180 degrees. It's just that what we do is we do it as if it's positive, so we just do E times the area, but then we just look at the sign of the charge. If it's negative, it's towards the charge. If the charge is positive, then it's away from the charge. So we just do it that way. We could do the same thing over here. Just say G times the area of the surface of the Gaussian surface, and then at the end say, oh, it's towards the Earth, right? Because it's. But I'll just put it in there anyway. This way, notice that this sign cancels this. So this is G. Now, what's the sum of all the area elements around the surface of the Earth? It's just the area of the Earth. What is the surface area of the Earth? Thinking of it as a sphere. What's the surface area of the Earth? Already sphere?
4 pi r squared.
4 pi times the radius of the Earth squared, right? The minus cancel, right? And then I have 4 pi g times the mass of the Earth. The 4 pi's cancel, and then g becomes capital G times the mass of the Earth over the radius of the Earth squared. So if you, and when you evaluate this for the Earth, right, you do 6.67 times 10 to the minus 11 times the mass of the Earth, which is 5.98, times 10 to the 24 kilograms. The radius of the Earth is 6,378 kilometers, so I'll convert it to meters. But then I gotta square it, right? When you do this, you end up with 9.8 meters per second squared. And by the way that we obtain that result, can I erase this?
Yeah.
The way that we obtain that result in Physics 185 was by saying the following, right? We used Newton's second law of motion instead of a Gauss's law type of equation, right? So we said that the net force acting on an object is equal to the mass times the acceleration. But if the object is in free fall, then the only force acting on the object is the force of gravity. So we made this just the force of gravity, because that is the definition of free fall. Yes? And then we said, okay, I'm going to take this and I'm going to plug it in here. So this becomes the force of gravity is equal to the mass of the object that is in free fall times the acceleration of the object. Well, that would be the free fall acceleration of the object, right? Right? So if the only force acting on the object is the force of gravity, the resulting acceleration is the free fall acceleration, right? And then what do we know about the force of gravity? In fact, it's right here. So if the object is over here of mass m, right, then close to the surface of the Earth, so that we don't have to worry about this height over here. You know, that correction is minute. So then you would have, what is the magnitude of the force of gravity? It's the universal gravitational constant times the mass of one object, which is going to be the mass of the Earth, times the mass of the other object, which is the mass of this thing that's in free fall, divided by how far the object is when it is close to the surface of the Earth from the center of the Earth, which is just the radius of the Earth squared. And it's down towards the center of the Earth. And that's this force, right? On the right-hand side, we have the mass of the object times the free fall acceleration. And then the mass of the object cancels, and we get that the free fall acceleration of the object is capital G times the mass of the Earth divided by the radius of the Earth squared, and it's down towards the center of the Earth. And this here is this. So you just call it G towards the center of the Earth, which is 9.8 meters per second squared down. So this is how we teach it in Physics 185. Because when you take Physics 185, well, you're required to at least be in Calculus 2, but not necessarily, you're not forced to be in Calculus 3. And in Calculus 3 is when you learn about, maybe, what's the area vector of a sphere, of a cylinder, and stuff like that. So then you don't learn it like this. You learn it from F equals ma. You can get it, right? And you get 9.8 meters per second squared down towards the center of the Earth. But we can use not just F equals ma to obtain this result for the free fall acceleration of an object, as long as it is near the surface of the Earth, right? We could also use an analog to Gauss's law. And the reason why I'm going over this problem, in addition to providing you with yet another, derivation of that result, is that in the case of the Earth, this is not like the case of the metal. In the case of the metal, in electrostatic equilibrium, if it has any charge, it goes to the surface. But the Earth, doesn't have the mass that just goes to the surface. The Earth has mass everywhere inside. So the Earth is like a dielectric, an insulating material. Inside the Earth, there is a gravitational field. And if you plot the magnitude of the Earth gravitational field, just the magnitude, let's forget about the minus sign because that's just indicating direction. If you plot the magnitude of the Earth gravitational field, with depth in the Earth, this is R, that's the radius of the Earth, right? This is 0. This is just the magnitude of G, so that I don't deal with minus signs, right? It turns out that the gravitational field is linear with it. Well, roughly linear if you assume that the mass distribution is uniform, but it really isn't. And then it goes as 1 over R squared. And this point of view here, when you're close to the surface of the Earth, that's 9.8 meters per second squared. So inside the Earth, the gravitational field of the Earth is less than 9.8 meters per second squared. Outside the Earth, the gravitational field is less than 9.8 meters per second squared. So this is inside the Earth. And this is outside the Earth. The astronauts, when they used to ride in the space shuttle around the planet, right, they would go to a height of 350 kilometers above the ground to make sure that they were not going to be moving through the air. Make sure that there's no air out there, because then you would have air friction and that would slow down the space shuttle. And so at their height, this is the 350 kilometers, 250 miles or so, right? The gravitational field at the height of the space shuttle is like 9 meters per second squared. Yet you look at video footage of the space shuttle with the astronauts in there, and it's like, this marker is floating, and people say, oh, there's no gravity. Those of you who have taken Physics 185 from me, we had that discussion, I think. But there is gravity. There is gravity. If it wasn't for gravity, the space shuttle wouldn't go around the Earth. So what happens is they have a big rocket booster. Here's the space shuttle. And, let's say it's this one. And they have 2 smaller rocket boosters. Thinner, 2, and then a big one. You've seen pictures of the space shuttle, right? And then when they take off from usually Cape Canaveral in Florida, they go, it starts from Brest. So it goes, it's gotta be amazing. Has anyone ever seen that takeoff in person? I've never seen it. It'd be cool to see it someday. And I hope it doesn't explode. Because that must have been, I'm glad I wasn't there. So, my goodness. So anyway, it goes, And then it starts to go like this, right? There's a reason for that. And then it goes, "Arr!" And also there's a reason why they do this next to the ocean. Because these two guys use up their fuel before the big one. And as soon as they use up that fuel, it's just extra mass that you don't want to carry. So you throw it away. Whales, sharks, get out of the way. And people, "Oh, I'm going on a cruise to Bahamas. Be careful." So anyway, and then this one still has fuel, so and when this one runs out, and then this one, you hope that by then, this one is going at 17,500 miles an hour. At that speed, and it doesn't help to just go, because then you're gonna, boom. Because at that speed, right, when the space shuttle is like this, going that fast, they don't have any more rocket boosters. There's nothing kicking anything like, I'm going forward, I'm stepping on the gas pedal. No such thing. They all go, they fall asleep, it's not an autopilot type of thing. There's, so what happens is that they better be going fast enough, because then they're, the space shuttle has a motion no different from this. If I throw this, well, it landed over there, right? If it goes faster, it lands farther away. And if I throw it so that it goes faster, it lands farther away. So the idea is that the space shuttle is going fast enough that it's falling, but because it's going so fast, then, it goes around the Earth, because then the Earth turns. Well, it doesn't turn, it curves.
Hopefully it doesn't hit it.
So then it curves, and so it's like the space shuttle says, I want to hit you, but you keep getting away from me. And the thing ends up going around and around. And at that speed, they can go around in 91 minutes. And so, of course, they're in free fall. They are in free fall. At that height, the acceleration due to gravity is 9 meters per second squared, not 9.8. But they're in free fall. So imagine if I go to the top of a building, Empire State Building House, and I have this thing with me, and I say, I'm going to jump. And when I jump, I go like this, and I let go of that thing. As I go down, what is that thing going to be doing? It's going to be right next to me. Oh, it's floating. No gravity. Yeah, right. No gravity. It's gravity that's making me go down. But from my point of view, the thing is floating. And you get the impression that if I were to film that, oh, wow, weightless. No gravity. Wrong. There is gravity. It's gravity that keeps the space shuttle going around. It's just that it's going so fast that it keeps missing the Earth or the ground. The Earth goes around the sun and it's in free fall. Luckily, it's going fast enough that it doesn't hit the sun. Sometimes we get closer. Actually, that's in the wintertime. And sometimes we get farther away because the orbit is not circular but elliptical. And the sun is at one of the two foci of the elliptical orbit. But if, for whatever reason, the Earth were to slow down, that's it. It would just fall straight into the sun. And as we get closer and closer to the sun, it will get bigger, bigger, hotter, hotter. Ah, we burn. So that wouldn't be good. So, if you go closer to the surface of the Earth's gravitational field is going to get smaller. If you go farther away, it's going to get smaller again. Okay? Anyway, so if anything, there's a connection between, there is a Gauss's law for gravity. It's just that you're not introduced to it in physics 185. But there is one. You can still get G anyway from just F equals ma, right? And the free fall acceleration, did you wonder that, it doesn't depend on what the thing is that's falling, if it's this eraser or a marker? It's because this mass cancels this mass, so it doesn't matter what is in free fall, as long as it is in free fall. And why near the surface of the Earth? Because we're forcing the distance to be roughly the radius of the Earth. So anything inside the Earth atmosphere it's pretty much, 9.8, right? So the height of the Earth atmosphere is maybe 20 miles, 30 kilometers, and 99% of it is, it goes down a little bit, but not so much. Good? Are we good?
Yeah.
Yeah. By the way, so they want to be going fast enough to keep hitting the Earth. But what would happen if they did that in the Earth's atmosphere? For one thing, there's going to be friction, air friction, and at that speed, air friction is going to be big, and it's going to slow it down, and then boom, it's going to hit the Earth, and that's it. Right? So not good. Or they might be going, oh my goodness, Mount Everest, boom, they hit Mount Everest, right? Bad. They still have the problem of coming back to Earth, and at that speed, air friction is big, and when they re-enter the Earth's atmosphere, they gotta turn on some rockets and shoot something that way so that then they get pushed this way. And so then when they re-enter the Earth's atmosphere, that's why they hire the best pilots in the US Navy or Air Force, right? There are two types of astronauts. The ones that do science experiments while in space, and then they're the ones who drive the space shuttle, right? The pilots. And those, they have to be very, very, very good, right? Because they have to be coming in at the right angle, because at that speed, there's a lot of air friction that they encounter as they re-enter the Earth's atmosphere. And, the force of friction is this way. The displacement of the space shuttle is this way. The angle between the displacement and the force of friction is 180 degrees. So the work done by the force of friction is negative. And what that's doing is it's taking away mechanical energy from the space shuttle and converting it into thermal energy. So it gets very hot outside the space shuttle. I met once Franklin Chang Diaz, and he flew in the 1980s, one of the first few missions of the space shuttle. And he was telling me that, wow, when they re-enter the Earth's atmosphere, he could just see fire out the window. Pretty much. And it got inside, it got like 125, 130 degrees Fahrenheit. It was, it's scary. And I don't know if you know, but one time it disintegrated coming in. So one of them was lost. I think it was the Columbia one. And then the Challenger, so the two of them have exploded, right? Or lost. One of them was the Challenger was on the way up, and the other one was re-entering the Earth atmosphere, right? So you need the best pilots and conditions and so on. The panels that they put on the surface of the space shuttle, they're like very special materials to withstand, strong enough to withstand that the environment outside, cold and also the extreme high temperatures as it goes back in, as air friction converts mechanical energy in the space shuttle into thermal energy. So anyway. So I said that was an aside, so sorry about that, but. Okay, so then, can I erase this part?
Yeah.
Here in Downey, they had a lab where they used to put those panels on the space shuttle. And
Was it heat shoes?
yeah, and they're like maybe the size of this, and one by one all around. And so when I was an undergrad, the City College of New York, which is where I went for my undergraduate degree, they have the second largest planetarium in New York City. The largest one being the Hayden Planetarium, which is in the Museum of Natural History. But City College has the second largest one. And the professor in charge of the planetarium asked me to work in it. And I said, cool, I'll do it. And so I used to run the planetarium shows at the City College of New York. It was really nice. At that college, they have something that I wish OCC had and UCI had. And it's the following. At the City College of New York, there are no classes, nowhere in the college, every Thursday from 12 to 2 p.m. No classes. They're called club hours. So, we used to organize like soccer, tournaments, and you form a team with your friends, and then you compete, right? If you didn't like that, then there were talks given by professors, on different subjects, and you could go listen to a seminar. Or you could go to the swimming pool and swim, or you could lift weights, and they had famous orchestras come in and play outdoors, and so it was you could choose, or you could study, or whatever, right? So, but there were no classes, right? And that's when I used to show, that's where I used to work in the planetarium during those 2 hours for the college. So on Thursdays from 12 to 2, I would present the show at the planetarium for the college community. All the students, professors, whoever they wanted to come in, right? So on some, whatever. But then during the week, we also hosted little kids from kindergarten, elementary school, middle school, high school. They would come in, like a school trip, and then they would come in, and then I would show them the shows. And so NASA has an office at that college, which is dedicated to preparing teachers, elementary school teachers, middle school teachers, high school teachers. They had a lot of resources for the teachers. And the guy from NASA came to me and asked me, I want to bring these teachers, and would you give them a show? And I said, yes, of course. And so I did, and they brought a few classes also, and so yeah, of course. And then he said to me once, I'm so grateful that you've been helping out with this. We're organizing a trip to California, okay, and we're gonna go visit the one of those places where they do work on the space shuttle. You want to come along, and you can bring someone with you if you want. So we're gonna go in a U.S. Navy plane, and the hotel, we are gonna cover half of it. The only thing you have to pay is the other half for the hotel. Cool. So I came with my girlfriend, who now is my wife. And so we came in a U.S. Navy, airplane. They wouldn't tell us where it was going to be leaving from and so on. There was all of this.
You just believed him like that?
Yeah, so, okay, I'm going to California. That was my first trip to California. And they brought us to Downey, and then we went into the plant, and we went in a space shuttle, and we checked, and they were telling us about those panels that they did that work over there. And that's how I learned about it. So I remember we stayed at the LAX Hilton. And then I went back.
You go surfing?
Huh?
Go surfing?
No, we went to Manhattan Beach, yeah.
Oh, okay.
But we didn't have surfboards already, but we did go in the water, yeah. So it was fun. Muhammad Ali was at the hotel, I remember. Met Muhammad Ali. Pretty cool. Yeah. Anyway, that's another story.
Didn't they build like James Webb around here? The new telescope?
The what?
Didn't they build James Webb around here, like up in Redondo Beach or something? I feel like
Yeah,
they built
I wouldn't be surprised. Yeah, California has they do a lot of these. I mean, those projects usually they build parts here, parts in Texas, parts in other places. Anyway, so that was nice. The question is, how the hell did I end up in California? Right?
Yeah.
So I went with my girlfriend at the time. We drove to Florida because I was tired of the cold weather in New York City, and I said, well, as great as New York is to visit and so on, I'm just tired of the cold weather. So I drove to Florida and I visited various schools in Florida. I was trying to go down south, warmer places, right? And I went to the school in Tampa, Gainesville, Orlando, one in Miami. I mean, I really liked Miami. There's an ED at the end. And I was interested. When I was at the University of Miami in Coral Gables, I was walking around the campus, and I saw an office of a professor, a physics professor, and I started chatting with him. I'm interested in going to graduate school here and so on. And he says, oh, and then we started, talking, asked me a few questions, and it turns out that I had a copy of my transcripts, and then I showed them to him, and he said, you know what? With your grades coming to Florida, any school in Florida, from the City College of New York, you're stepping down. And you have good grades, so you should go to a better school than City College, if anything. I was thinking a lot when I was driving back to New York City. That one comment by one person. I mean, I was only focused in schools in Florida. And went back, and about 3 weeks later I said, you know what? I'm gonna listen to him. So I didn't apply to any schools in Florida. And then I said, well, South, good schools, California. And then UCI opened the doors, and so I came to UCI for graduate school. They made me a good offer, blah, blah, blah. So it worked out, yeah.
And now we got the best physics teacher.
You're getting an A. So it's amazing how there are points in your, times in your life where, a comment can really, change your whole future, right? I mean, what would have happened what if he had not been there? What if he had been in the restroom or something, or the door was closed and I didn't speak to him? Then I probably would have applied to somewhere in Florida and be there. I mean, maybe that would have been very nice too, but it's just amazing how I remember when I was like in my third year in college, my thermodynamics professor, we were talking in his office, and he said, yeah, well, maybe someday you'll like to go to California. And deep inside I said, yeah, right. I mean, who is in California? I don't know anybody in California. It's amazing, right? So anyway, more physics, sorry about that. Okay, so is it 6?
Isn't it 5?
Five.
I think the last one was 4.
So we'll do the infinitely long wire, no width to it, with uniform charge per unit volume, per unit length, lambda. So lambda is the charge in 1 meter of length of this wire. So it's infinitely long, or very, very, very long. That's what it is. So the charge per unit length is lambda. That means that if you consider, if this is 0 and this is 1 meter, the charge in here is lambda. The charge in 1 meter of length of this wire. And I want to know what's the electric field there. You know, some distance away from the axis. Okay, so right there, say. What is the electric field there? So now we're going to consider a different Gaussian surface. What is the Gaussian surface that we should consider? If we are given a wire? A cylinder. So the cylinder that we are going to consider is this. The surface of the cylinder has to be passing through that point where we're asked to calculate the electric field. And then remember that it's going to be a closed surface, right? So I have to consider the faces of this Gaussian surface, cylindrical Gaussian surface. So this thing over here is the Gaussian surface. And I'm going to do this in detail. And then every time I do another cylinder or wire, I'm going to take the shortcut. Like we did for the case of the spheres, the E dot dA just became E times 4 pi r squared. Now it'll become, you know, something different. I mean, and you'll see. So, and you know, let's say that this charge is positive. Let's just say it's positive, right? So we have charge all over the place. Now, this surface has, or this Gaussian surface has 3 parts to it. I'm going to split it up into 3 parts. There is this face over here, which I'm going to call face number 1. You know, that face. Because I got to consider the whole Gaussian surface and it's going to be closed. So I got to consider this face. I have to consider this face. I'll just call it face number 2. And the round part, right? So essentially, if this is the Gaussian surface, this is face number 1, right? That one is face number 1. This one is face number 2, but I gotta consider the curved surface, right? So then this is, I'll call it the curved surface. So when I write down Gauss's law, it's this. All right. I have to do, what does the circle here mean? It means that I have to do this integral over the entire surface, right? So I'm going to split this integral over the entire surface into 3 integrals. I'm going to write E dot dA over face number 1 without the circle, because face number 1 is not closed. It's just, you know, this circle here, right? Plus E dot dA over face number 2 plus E dot dA over the curved surface equals Q enclosed over epsilon naught. All I did was split up the integral of the electric field over the entire Gaussian surface into 3 integrals. Yes?
And you didn't put the circle through the integral because each of those on their own is not a closed.
Exactly.
Okay.
Exactly right. Exactly right. Each one of those is open. Right? There's a way to go to the other side without having to go through the surface for each one of those. Now, so let me consider the electric field on face number 1, the electric field on face number 2, and the curved surface, right? So let's just work on the electric field. What is producing the electric field, remember? What's the source of the electric field in the problem? The wire, which is charged. And if the charge is positive, the electric field is away from the charge. If the charge is negative, the electric field is pointing towards the charge, right? So at this point, what is the direction of the electric field? away from the charge. What about over here? Down, away from the charge, right? What about in this phase? Away. Away from the charge. Right? What about over here? Away. What about here? Away. And here? Away. Don't confuse the area vector with the electric field vector. Right? All we need to remember is the basic idea. If the charge is positive, it generates an electric field pointing away from it. If the charge is negative, it generates an electric field pointing towards it. That's what you need to remember. Right? So the charge is positive, it's just away, away, away from the charge. Now, those are these electric fields. What about the area vectors? What do we need to remember about the area vector? Well, it's got to be perpendicular to the surface, right? And going outwards or inwards? Outwards. So what will be the direction of the area vector over here? Going outwards, and so which one would that be? And perpendicular, right? What about for this point over here when I consider the integral over that? Yes? What about here on phase number 2? To the right, correct. Perpendicular to the surface and going outwards. What about over here on phase number 2 at this other point? To the right, correct. Perpendicular to that face. Right? What about here on phase number 1? Area vector, which way is it pointing? To the left. That's perpendicular to that surface and going outwards. And here, to the left. Now, notice that I have dot products, right? The dot products means that I need to consider the cosine of the angle between the electric field vector and the area vector. If I consider the curved surface, what is the angle between the electric field vector and the area vector? 0. What about over here? 0. Still 0. What about if I consider phase number 2? 9. Ooh, and the cosine of 90 degrees is going to be? What's the cosine of 90? And here is going to be for phase number 1. So, for phase number 1, the cosine of 90 degrees is going to be 0, and that'll kill it. Yes?
I just was a little confused on why E is perpendicular to dA for the faces.
So, let me draw this. That's the wire. What's the electric field here direction?
Up.
What about here?
Up.
What about here?
Up.
What about here?
Down.
What about there?
Down.
What about here?
Down.
What about here? Away from the charge. That has nothing to do with the surface.
Okay.
The electric field. Now, then you do the area vector.
Oh,
And that's perpendicular to the surface.
Yeah.
That has nothing to do with the charge. And then you gotta take the dot product between the electric field vector and the area vector for the different surfaces that make up your closed surface. But when you do the dot product, you're concerned with the angle between those two vectors, and you gotta take the cosine of that angle. So whatever the electric field is over here, it's something, the area vector is something, but the cosine of 90 degrees is gonna make it 0. No contribution from here. For phase number 2, what's the angle between these two vectors?
90.
Also, and the cosine of 90 degrees is gonna be 0, so it's like we get 0 plus 0, no contribution. Yes? Now, what about over the curved surface? What is the angle between the electric field vector and the area vector for all points on that curved surface? 0 degrees. And the cosine of 0 degrees is 1. So that will just be E times the A times the cosine of 0, which is 1, integral over the curved surface. And that equals, well, let's take care of Q enclosed. let's make the length of this Gaussian surface L. What is the total charge inside the Gaussian surface? Lambda times L, correct. The total charge is the charge from this face on the wire, right? Up to this face, because this charge over here is outside my Gaussian surface. This charge is outside the Gaussian surface. It's just a charge enclosed. So if the charge per unit length over here is lambda, and this length is L, what's the total charge in there? The charge per unit length times that length. I mean, if the charge per unit meter, per meter, is 2 coulombs per meter, what will be the charge in 10 meters of length? 2 plus 2 plus 2 plus 2, 10 times is 2 times 10. So it's just lambda L. By the way, what was the original problem? The original problem was simply, you have an infinitely long wire, right? The charge per unit length is lambda, and I want to know the electric field right here. Right? At some distance r away. There's no mention of L. L is something that I'm putting in myself. I'm the one imagining this Gaussian surface that doesn't exist. And I'm the one giving this Gaussian surface a length of L. So that L better disappear by the time I'm done with the problem. Because somebody else might imagine a shorter, Gaussian surface, right? And so how long of a Gaussian surface you imagine should not affect the final result. So I threw in an L, but I better not get that L in my answer. It has to cancel out. Yes? Okay, so I'm doing it in detail, then we're just going to jump from Gauss's law to some line, and then we'll take it from there. Okay. Why does choosing a curved surface like this, like cylindrical, why is that a good idea in this problem? Notice that it doesn't matter where I am on this curved surface, or even around, I'm at the same distance away from the wire, from the charge. So the magnitude of the electric field has to be the same. I have that symmetry. So therefore, this baby right here, I can slide it outside the integrand. So I get E times dA for the curved surface, which is, and this is the sum of all the area elements of the curved surface, right? Equals lambda L over epsilon naught. So, what is the area? What's the surface area of the curved surface of the cylinder of radius r and length L? What's this area? Think of it like this. Think of this ring. And then you have a whole bunch of rings. L of them. What's the length around this ring? 2 pi r, and then the height. And that'll fill that surface. And isn't that nice? Because we can cancel that. And that's the answer. So, with cylinders, very long cylinders and wires, we're going to take a shortcut. We're going to write this. That's Gauss's law. And instead of doing all of this again and again and again for every problem, we'll just remember that the Gaussian surface that we use is a cylinder, right? And we'll remember that the faces do not contribute. The only surface that contributes that's important is the curved surface. So then from there we're going to jump to here. So Gauss's law will be one line in an exam quiz, whatever. That will be number 2. And then here's the answer. So you can take the shortcut. But I want to go through the steps of how you get from here to number 2. I want to go through this argument over here. And then we just take the shortcut. can do that one too. Should we do that one next? If you,
Low, maybe get
Huh?
later.
I can do it right here. We don't need too much. So she's saying, what if you have a sphere that's hollow, nothing in there, vacuum, radius A, radius B, and it's a dielectric. So there you can have charge distributed throughout. And suppose the charge per unit volume is rho, and it's uniform. So and then we have vacuum over here. So vacuum outside, dielectric. I'll do it like this so it's easier to see. The vacuum. And there are three regions of interest over here, right? I want to know, and there's nothing at the center. There's nothing, right? So I want to know what is the electric field here, there, and there, right? There are three regions of interest, right? And this is a hollow. We could almost do this in our head. Almost. Almost. If I ask you, what is the electric field right here? At point number 1, point number 2, point number 3. Let me do point number 1 first. That would be R less than A, correct? So I would write E dot dA equals Q enclosed over epsilon naught. So this is E times. What would be the Gaussian surface that I would choose? Like this, right? Or radius R, right? Yes? So I multiply that by what? 4 pi R squared. And what is the total charge inside of that? What is it? 0. So electric field is 0. Yes. Number 2, here, point 2. This is more challenging. Less than B, but greater than A. So, Gauss's law. So now in that case, can I erase this? Can I erase this? Maybe I'll erase this and it will make it easier to see. So we have this and this, A, B, and I want to know the electric field here at a distance r from the center, and this is my Gaussian surface, right? So I take E at the Gaussian surface, multiply by what? 4 pi r squared, correct? And before I forget, I do that. Now, what is the total charge inside of it? So the total charge that I want is this charge. In blue, right? That's what the charge is. Inside the Gaussian surface, right? Because this is vacuum, right? There's no charge over here. So it's only that charge. So it would be the charge per unit volume times that volume. So what is that volume? What's the volume in blue?
4 pi r squared minus 4 pi a squared?
Volume. There's a third and a cube. Volume is 3 dimensions.
Oh.
So not square.
4/3 pi r cubed?
4/3. So what would it be?
4/3 pi r cubed minus 4/3 pi a cubed.
Say it again.
4/3 pi cube minus 4/3 pi a squared. Pi a cube.
Exactly. Good. So is the volume of the sphere in red minus the volume where it's empty, or radius A? It's just the difference of the two volumes, right? What's the volume between two spheres? It's the volume of the big sphere minus the volume of the inner sphere. And then what you have, that's this volume, right? So then the 4 pi's and the 4 pi's and the 4 pi's cancel, so you get E times R squared equals, and then you have this, right? You have a 3 and a 3 and a row 3, and then you have here R cubed minus A cubed. And then bring the R squared downstairs. That's just another line. So instead of 1, 2, 3 lines, you get 1, 2, 3, and then another one. So it would be this. And what would be different if we wanted to know the electric field over here? Where now this is R. So now our Gaussian surface is going to be this, right? So that would be what? E times what? What area should I multiply that by?
4 pi r squared.
4 pi r squared. And then what should I have in the numerator?
The
I want all of this charge now, right? But only up to, I'm sorry for the mess.
4/3 pi.
Let me do this again.
Oh.
That's what the charge is, right? And my Gaussian surface is this. So this is C, R greater than B. So what's the charge enclosed?
4/3 pi b cubed minus 4/3 pi a cubed.
Times rho, right? Times the charge per unit volume. And then the next line is the answer. So the 4 pi, so you get that this is going to be rho b cubed minus a cubed over 3 epsilon naught r squared, right? Something like that. Yes? It's still, this one is still 2 lines. Boom, boom. But it's just finding the volume between two spheres. It's the volume of the bigger sphere minus the volume of the inner sphere. Okay, can I erase this now? So, what are the only 2 Gaussian surfaces that we imagine?
Why is it 4 pi r squared and not e squared?
Because over here it's E dot dA. Here I want the area of the Gaussian surface. And that's, for a sphere, 4 pi r squared. Now here I want the total charge inside, which happens to be distributed over a volume. So it's the charge per unit volume times a volume. And that one has the R cubed. No? So if you have a, so in fact that's what I was going to say now. What are the only 2 Gaussian surfaces that we imagine? spheres and cylinders. So, and you know, in Gauss's law, you're gonna have an area, so you should know the area of a sphere and a cylinder. And when you consider this, you might have charge distributed over an area, over a length, or over a volume. So you should know what the volume of a sphere is and what the volume of a cylinder is. You should know what those formulas are. Because you use them over here. So for example, if you have a sphere, of radius r, what's the area of it on the surface for a sphere?
4 pi squared.
4 pi r squared. And what's the volume? What's this volume?
4/3 pi r squared. Pi r cubed.
4/3 pi r cubed. In fact, if you have trouble remembering this, remember the volume. What if you take the derivative of the volume with respect to r? Do this. What do you get? You get the area. So that you remember how to do, right? Take derivatives. So if you're like, oh my goodness, I get confused, then just remember the volume. Differentiate it, and you get the area. As a, you know, if you want a shortcut to that. Now, what if you have a sphere? I'm sorry, a cylinder.